Right, here's our second video in 5.5. We just got done looking at some basic sum and difference of cubes problems. Let's get a little more complicated, a little more challenging with some of these problems that may or may not be cubes. In example number 2, it asks us to factor, so make sure you're still following the steps. Is it in order? It's kind of hard to tell if you have x's and y's, so hopefully it is in order. Is there a GCF? I don't see one. I do notice that there are two terms, so this is either a sum or difference of cubes or a difference of squares. If I tried squares, is 125 a perfect square? Is there a square root of 125 that works out evenly? Or is x cubed a perfect square? Can I divide 3 by 2 equally? Well, it doesn't look like it, so that's how I know it's not a squares problem. So let's see if it's a cubes problem. Now remember, in order for it to be a cubes problem, we have to have a base that's cubed and then another base that's cubed. And right now, the only thing that I see that's cubed is really the x. And I want to make sure that the whole thing is cubed so that it follows into my formula. So I've got to change this 125 so that it's something cubed. So what cubed gives me 125? Did you say 5? So really, instead of saying 125x cubed, could I really say that that's the same thing as 5x, the whole thing cubed? That means the 5 is cubed and the x is cubed. That way, I have a base that's cubed. Now I need to make sure that the other base is cubed. So, y to the 6th power, we've got to make that into something cubed that's equivalent to y to the 6th power. What we can do is we can take that y to the 6th and divide it by 3. So it's 6 divided by 3. Woo! See if I can, no, I'm deleting stuff. You should end up getting y squared. Now remember, when we raise to a power, we really multiply the exponent, so 2 times 3 should give me 6. That makes sense, right? But now I have two bases that are cubed. This is my first base, 5x. This is my second base, y squared. Now let's use our formula for the difference of cubes. Remember, we start with a small parenthesis, and then we have a big parenthesis, and then we're going to do our signs. It's the same sign, so minus, opposite sign, so plus, and then the last one's always going to be a plus sign. Now let's fill in the blanks. It's my first term, which is the 5x, my second term, which is the y squared. It's my first term multiplied by itself, so what's 5x times 5x? Did you say 25x squared? It's not a 5x squared. Remember, the 5 and the x has to be multiplied again. So 5x times 5x is 25x squared. Now it's the two terms multiplied together. So I should have a 5x times a y squared. I don't know where my squareds went, so be careful there. You should have a 5xy squared. And then it's my last term multiplied by itself. So what's y squared times another y squared? You should get, look at me messing up here, you should get y to the 4th. All right, let me write that a little bit better. You should have a 5x minus y squared. You should have a 25x squared plus 5xy squared plus y to the 4th. And then if you were to FOIL that all out, a lot of your terms should cancel, and you should end up getting 125x cubed minus y to the 6th. So be careful with all your exponents. Even I mess up, so be careful with that. All right, look at B. Is it in order? Looks like it. Is there a GCF? Is there a number I can divide evenly into 27 and 125? I don't know if there is. So let's see. It looks like there's two terms and there's a plus sign in between, so I know it's not a difference of squares. Let's see if it's a cubes problem. I need to be able to write both of these as a quantity cubed. Now it looks like to me the only thing that's cubed right now is the z. So we need to turn the 27 into a cube and a 125 into a cube. So what cubed gives me 27? Yeah, so I'm going to write it as 3z, that quantity cubed. That would be the same as the original problem, but now I have a base that's cubed, and I can use my formula a little bit better. And what cubed gives me 125? 5, right? And so my two bases would be the 3z and then the 5. So let's use our formula. Little parenthesis, big parenthesis. Let's start with our signs. Same, opposite, always positive. Soap. Now let's fill in our blanks. We have our first term, which is our 3z. We have my second term, which is my 5. I have my first term times itself, so 3z times 3z is 9z squared. I have the two terms multiplied together, so what's 3z times 5? Could I really say 15z? And then what's 5 times 5, or 5 squared? We're going to say 25. This should be the factored version of my original, using my sum of cubes. Let's do two more. In order, GCF, it looks like two terms. So here we go. I'm going to write this m to the 6th power as m squared, right? And then I'm going to write the 64 what times what times what gives me 64, 4. And so now I have two bases that are raised to the 3rd power. I hesitated there for a second because I thought maybe this could be a squares problem, because isn't there a square root of 64? And can I take m to the 6th and break it down equally into an m cubed and an m cubed? But then I noticed the plus sign. And so remember, squares only works if it's a subtraction sign. A difference is squares. So that's how I knew it wasn't going to be squares. All right, let's keep going. So we have our two bases. We've got our signs in there, same, opposite, always positive, and then let's fill in the blanks. We've got an m squared, we've got a 4, we've got an m squared times an m squared, that's an m to the 4th. We've got an m squared times a 4, or a 4m squared, and then we have a 4 times a 4, which is 16. So my final answer factored should look like that. All right, let's look at D. Is it in order? Is there a GCF? Hopefully you took out that GCF first. If you didn't, you'd be kind of stuck, because 3 isn't a perfect cubed and 192 isn't a perfect cubed. So if you take out that 3, let's see how that changes things. If you GCF out a 3, your binomial that's left should be an x cubed plus 64. That looks a lot better. I know there's only two terms, and I know it's not a difference of squares because of that plus sign there. So let's see if we can write it as a cubes problem. So I should have an x cubed, and then what cubed is 64? 4, right? And so now I have my two bases that are cubed, and I can use my cubes formula. Same, opposite, always positive for my signs, and then I can fill in the terms. Don't forget your GCF out in front. You should get a final answer of 3, x plus 4, and then an x squared minus 4x plus 16. Don't forget your GCF on that one. Makes it a lot easier if you do that first. All right, take a few minutes, try these two, and then check your answers with mine when you're done. All right, this first one is a sum of cubes. You should end up getting an m plus 5, and then an m squared minus 5m plus 25. The second one, there's no GCF. It looks like it's a difference of cubes. You should have factored this one into a 3x plus 1, a 9x squared plus 3x plus 1, making sure that you have a 9x squared and that first term in the second parentheses. All right, hopefully you're getting a hang of sum and difference of cubes. We've learned a lot of different factoring strategies, and in the next couple of sections that are going to be all jumbled up, so it's really important that you get a hang on each one individually so that when it's all jumbled up, you have a good solid foundation of all the different factoring techniques. All right, keep working hard.